Coulomb's law, or the Coulomb's force, or electrostatic force. So this chapter is about the electric field. So there are many sections in this chapter. The definition of the E field, and then we will try to calculate the E field due to charge, particle, dipole, line of charge, charge D's, point charge in an electric field, and also dipole in electric field. So there will be more integration in this chapter. So you may feel more difficult than the previous one. So first of all, the electric field. Last time we know that as long as we have two charges or two pack of charges, then we know there will be force acting on them. If they have the same sign, they will repel each other. If they are in opposite sign, they will attract each other. Now, a question is, since the particles do not touch each other, how can the particle 2 push particle 1? How can Q2 push Q1? We know that there is a force repelling them, but they don't physically touch each other, but still they push each other away. So how can there be such an action at a distance? So we introduce another concept called the field. Maybe you have already learned it in the mechanics, because there is something like the gravitational force. Then suppose there are two mass, and then they will attract each other, similar to the Coulomb's force. So we try to define a variable called the E field, the electric field, or usually I will call it E field. Simply, so particle 2 set up an E field at all points in the whole space. As long as there is a particle, no matter if it is a positive charge or negative charge, it will set up a field at all points in the whole space. Of course, particle 1 will also set up a E field, but let's consider particle 2, and if we place particle 1 at any point in that space, actually the whole space, so no matter where you put Q1, particle 1 is in that space, and particle 1 knows the presence of Q2 because it is affected by the E field due to the particle 2. So particle 2 push on Q1 not by touching it, as you would push on a coffee mug by making contact. So instead, particle 2 push by means of the electric field it has set up. So Q2 push Q1 not by touching it, but through the electric field. Simply say. So here we legitimately define the E field at any point in terms of the electrostatic force, or the Coulomb's force we learned in the previous chapter, that would exert on a positive charge Q0. So suppose we have a positive charge Q0, but how large Q0 is not really important regarding to the E field. So the E field is defined by the force divided by Q0, and that's the fundamental definition for the E field. So here we need to care about is Q0 is positive, so when we calculate the Coulomb's force, it is also positive. And if Q0 is negative, uh, F will be negative and divided by negative, so it is still positive. So, and if Q0 is larger, F is also larger, but they will cancel each other. So it turns out the E field generated by this charge is not influenced by this test charge. So we call it test charge. No matter how large it is, or no matter it is positive charge or negative charge, uh, this E field generated by this charge only depend on it. And the SI unit for the electric field is Newton per Coulomb. Newton per Coulomb. And in chapter 24, you know another SI unit for the E field is volt volt per meter. But it's just fine. You can choose either one. So here we will introduce another concept called the E field line, electric field line. Help us visualize the direction and magnitude of the E field. So it's just you can just see the electric field visually. You can tell, oh, this part has a stronger E field in magnitude, and this part has a weaker E field in the magnitude. So there are two rules. The first one is E field vector at any point is tangent to the field line through that point. So for this case, the line is straight, so the tangent line is the E field line itself. So you can see this charge is a negative charge, so all the E field line points to this this charge, and of course the E field all point to this charge at any point in the space. And for this one is a parallel, is a plate, is infinite plate. So the E field generated by this plate is not perpendicular, perpendicular to this plane. So E field is pointing to the right at this side, pointing to the left on this side. There may be some more complicated situation like this, but I just mention it later. So the density of the field line, the second rule is that the density of the field line is in that region is proportional to the magnitude of the E field there, which means that if you see the line is more dense at the region, then the E field is stronger at that region. If you can see the E field line is less dense, then the E field at that region is weaker in magnitude. And yeah, there are two more statements here. The force on a positive test charge near a very large non-conducting sheet with uniform positive charge on one side. So this is a so this is this figure. So this is a non-conducting sheet with uniform positive charge on one side. So it will generate the E field perpendicular to it, and actually we'll derive it later in this chapter. And also we will explain it again in the next chapter using the Gauss law. And so let's continue on the E field line. So extend away. So the E field line always extends away from the positive charge and goes to the negative charge. So you can see here there is two positive charge. So all the E field line are coming out from the charge. And actually, if there is only one, if there is only one charge, if you just ignore the bottom one, it will just look like this, but all the arrows are pointing outward. But here, if there are two charges, two positive charges, then you can feel that actually suppose we consider the point at in the middle. Suppose we consider the point in the middle. The E field generated by this charge will be pointing downward. So we draw it here, and we change the color blue. So the E field generated by the bottom charge will be pointing upward, and in the middle point, then they should have the same magnitude but in opposite direction. So these two will cancel each other, which means that the overall E field at this point should be 0. So you can feel the E field line is there's almost no E field line in between. So which means that almost all the E field are cancelled, generated by these two positive charges. So this is a visualized way to show the E field in the space. But actually, how large it is, you really need to calculate. You can only compare for example, for this region, the E field is weak, and for this region, the E field is strong, something like this. And actually, you can feel that these two charges are repelling each other, because you can see the E field line are something like this. So they can never attract each other, because suppose these two charges are fixed, and then you place a positive charge anywhere on this plane, then the charge should follow the E field line to go in that way. If I put it here, then the charge will possibly go here. And if I put here, the positive charge will go there. If I put a negative charge here, then the charge will go this way. So it is a visualized way to see if you put a positive charge, you will follow the E field line. If it is a negative charge, you will going backward. So up till now, is there any questions? It's only some basic concepts, so let's move on. So according to the previous definition, we can simply derive this equation for the E field. If I just have a single charge particle, because according to the Coulomb's law, it is nothing but so according to the Coulomb's law, it's nothing but Q0 R squared. Suppose this charge is Q, and we have a test charge here, Q0, and the E field at the point here should be the force, maybe pointing out downward or upward, depend on the sign of this charge. If it is a positive charge, it will pointing downward. So according to the definition we just written, so the E view should be F over Q0. So actually it's nothing but Q0 over R squared times 1 over Q0. And this one and this one is cancelled. So the rest of the stuff is something like this. So actually the E view generated by this charge is only related to the amount of charge and also the distance from this from these charges, and k is a constant. So if we write it in a vector form, it will look like this. And as I mentioned in the last chapter, R hat is a unit vector, and actually for this point, for example, for this point, R hat point to this way. If it is this point, R hat point to that way. So for different points in the space, R hat are different. This is the spherical coordination. 球坐标 spherical coordinate. Actually, you've learned it in the calculus class, I think. So here, so the electric field vector set up by the positive charge or point directly away from the particle, and those set up by a negative charge particle or point directly toward the particle. So it only relates to the charge itself, not related to the test charge. That's why we need to define the E field. It will make the math more simple. If more than one charged particle set up an electric field at a point, and the net electric field is the vector sum of the individual electric field. Electric field obey the superposition principle. So it's just like what I've mentioned here. You have two charge, no matter it is both positive or one positive, one negative, or both negative, then you can calculate the E field generated by this charge, and then you calculate the E field generated by this charge, and then for every point you add them together. But E field is still a vector, so you really need to use the vector sum to calculate the E field for the whole space, or at a single point, depend what you really want to calculate. Any questions? I suppose you have learned it in high school. So here is a graphical demonstration. You can go to this link. Go to this link to check this. I can show you a bit. Here. So I think I cannot open it in Google Chrome. I can only open it in Firefox because the Google Chrome does not support the Flash. So but it doesn't really matter. So here we can see it is a very simple simulation. So I think the only thing you can modify is the charge amount. MKZ is pretty strange. We can simply assume it to be a 1 unit of charge, 2 unit of charge, 3 unit of charge, so on. So you can see it here. If I make it 1 here, there are 3 arrows, and make it 2, there are 6. So just to show the electric field is stronger and stronger. So if I make it positive, this is to show the E field generated by this charge. So if it is positive, the E field is pointing outward. If I make it negative, all the arrows are pointing to the charge. So this is just what I mentioned. And I can actually place the second charge here if it is also positive, something like this. And you can see the green arrow, which shows the Coulomb force. If both of them are positive, then they're repelling each other. If one of them negative instead, then they will attract each other. If both are negative, they will repel each other. So we can deselect the E field line and show the E field. Let's make it. So this is the E field line. If I just place one charges with 4 units of charge. So in this simulation, for the darker arrow, which means that the E field is stronger. For the lighter area, the E field is weaker. So if it is positive, or the arrow pointing outward. If it is negative, or the arrow point to the charge. So let us make it something like this. If I have 2 positive charge with the same amount, then actually the E field line will look like this. Actually, they are repelling each other, and actually they are symmetric. The left one is just a mirror image to the right hand side. If I try to make the right charge smaller, so I make it 1 unit and keep the 4 unit for the charge 1, so that it is not symmetric anymore. You can feel that charge 1 try to push the charge 2 to the right hand side. So you can see something like this. And if I try to make this negative charge with the same amount, then actually we'll call it a dipole. I'll talk about it later in this chapter and in this course. So the E field line will be something like it starts from the positive charge, go to the negative charge, and is something like the coil of an apple. So it will be something look like this, something look like this, something look like this, and look like this. Actually, the magnetic field of the Earth is similar to this. It's something similar to this. So actually, you can play around with this simulation to get more feeling about the electric field. So let's take a sample problem. So here, so figure A shows 3 particles with charge Q1, Q2, and Q3. Q1, Q2, and Q3 with distance d from the origin. So this is 30 degree, 30 degree, and 30 degree. So what is the net electric field is produced at the origin? At the origin. So actually, this is quite simple. Quite simple. Well, so first of all, we calculate uh, E1 due to the charge Q1, which is nothing but K. The charge Q1 is 2Q, so 2Q over the distance is D. Distance is D. And actually, we can define R1 head to that direction, which is a similar, which is the same direction as this one. And for E2, for E2, it is still K, but here minus 2Q, minus 2Q, minus 2Q, and the distance is still D squared. It should be D squared. So here D squared, but here the unit vector for that one should point to this side, which means that the unit vector should be minus R1 hat, minus R1 hat. So so we have two negative signs, so it is nothing but K2Q over D squared times times R1 hat. So this is E2, and for E3, so we can define R3 hat in this direction. So E3 is K minus 4Q over D square R3 hat. Maybe we can define R3 hat in the other direction, following my notes. Okay, maybe I just define R3 hat in this direction so that we have a negative sign here, and then it will be something like this: K4Q over D square R3 hat. So everything have a positive sign. And actually, E1 and E2 are the same. E1 and E2 are the same. K 4Q over D square R1 hat. And we can find that this one and this one have the same magnitude, and actually you can find it like this: R1 pointing to this direction, R3 point to this direction, and 30 degree, 30 degree, 30 degree. So two vectors have the same magnitude, and then we can we can write it as E equals E1 plus E2 plus E3, which will be nothing but 2 cosine 2E3 cosine 30 degree in the x direction. So cosine 30 degree is square root of 3 over 2. So actually the answer will be 6.93 k q over d square in the x direction. Maybe I just erase that one. Uh, 6.93 kq over d square in the x direction. So this is the answer. So any question for this one? Or up till now, you can, if you have question for the previous page, you can raise also.有没有问题？有冇問題？冇啊。Okay, so let's move on. Okay. Okay. So so we talk about the electric field due to a dipole. If you have ever learned the chemistry, you know di means 2, and the pole means the endpoint. So in Chinese, this is called 拗字. But it doesn't really matter. So what is a dipole mean? It really means there are two charges. One is positive, one is negative. They have the same amount of charge, but they are placed very close to each other, but they will not move. So you will feel very strange. How come they will be? They have a negative. They have opposite sign, but they should attract each other, but they will never touch each other. They will still keep the distance like this, a small d, something like this. So let's go through here. Electric dipole consists of two particles with a charge of equal magnitude q, but opposite sign, separated by a small distance d. So this is the definition of a dipole. I suppose you have learned chemistry in high school, so you may have learned the hydrogen bomb. So something like, you know the water molecule, H2O. I suppose you should know. So in this case, you have O2 minus, you have H plus, something like this. And so they will have the bond between them. So actually, this is a positive charge, and this is a negative charge. So you can regard it as a, so you will equivalently as a dipole, something like this. This is a dipole pointing to this side, because if you just divide it into two, this is a negative charge, so you can regard it as a dipole. Like here, maybe I make it another color, so you can feel that there is a dipole in this direction. This is positive, this is negative, so that you can feel like something like this: positive, negative. And you have another dipole lying here, negative, positive. So a dipole is defined like this, defined like this, defined like this. So when you add them together, it will look like something like this. So this is the overall dipole. Then you can feel that actually the charge with a negative sign can still exist happily. So actually we'll define the dipole moment called P, which is also a vector, and it is equal to the charge Q, and the distance. So here we will define D as a vector. D is actually a vector pointing from the negative charge to the positive charge, So this is D vector. So this is the dipole moment. So the magnitude of the E field set up by an electric dipole at the distance point on the dipole axis, which run through both particles, can be written like this. We'll derive it in the next page. So, but similarly, it will look like this. And according to this definition, P equals QD, we can write it as 2P over 4 pi epsilon naught over z cube. Z is actually this axis. For this equation, we can only calculate the E field on this axis, but not in other space. In other space, rather than this axis, the expression will not look so similar like this. Only the point on this z-axis, which means that D is actually on the c-axis, which means the line connecting the two charges and then extend it. And this is the z-axis, and the positive direction is the positive charge side. So suppose Z is much larger than D, then the expression will look similar like this. And usually Z will be much larger than D, because I just mentioned a molecule. Then usually you concern the E field much farther away from the dipole, because the molecule, the bond will be so short, and you may concern the E field or much farther away. Maybe we just have a 10 minutes break, and then we'll go on.